So in this session, we'll discuss the MCQs related to topic magnetism. Figure 1 shows a vertical plane square coil which is having a 50 turns and carrying a current of 3 amperes. The length of each side is 4 centimeters. So each side is 4 centimeter long. Figure 2 shows the view of a coil from above, like looking from the top. The with the horizontal magnetic flux density or strength of a magnetic field is 0.20 Tesla. So what is the force on side Q and S? So whenever we need a force on the wire which is placed in a magnetic field, so the formula is F is equals to BIL sine theta. What about the theta? Because we are finding for side Q and S, so what will about the side Q and S? When we draw the magnetic field, like if this is the figure 1 is there, we are looking from the top, and this is basically view from above, and this is view from the side. So for side Q and S, the magnetic field lines are actually perpendicular 90 degree, and sine 90 is 1, or sine 90 is maximum, so the theta is actually 90, so this will be sine 90. L is the length, so length of this section, each section is 4 centimeter, but it should be in meters, so that's why 0.04. I is a current which is passing through, so 3 ampere is a current which is passing through. Strength of the magnetic field is 0.2, so strength of magnetic field is 0.2. So F is equals to BIL sine theta, where B is the strength of magnetic field which is 0.2 Tesla. I is the current which is passing 3 ampere. L is the length which is 4 centimeter or 0.04 meter. And the theta is the angle. Theta is the angle between the part of the wire and the magnetic field. So as you can see, because this is a side view, as they mentioned, P and Q. If you see, P and Q are making certain angle, but what about Q and S? How they will be there projected? So it will appear like this. This will be Q and S. So when you check the angle between the magnetic field and Q and S, the side Q and S, that will be 90 degree, because this side will be into Q and S. This is looking from the top, so side Q and S will be like this, into. So if it is into, it's a 3D structure. One is into and the magnetic field is pointing in this manner. So what is the angle between them? The angle will be 90. So when you substitute, you will get C as the right answer. So in this question, what is the unit of the magnetic flux linkage? Magnetic flux linkage is basically N phi. So N is a number of the turns which does not have unit, it's just a number, and phi is basically a magnetic flux, and magnetic flux is actually B dot A, or depending on the angle between the two. So you can also say the magnetic flux linkage is NBA, where N is not having any unit, N is a number, B is the strength of the magnetic field, magnetic flux density, also known as Tesla, and A is for area square, so it is Tesla meter square, or this Tesla meter square is also known as Weber. So when we check the option A, Tesla is not there because the Tesla is a unit for B. Tesla per square meter, that does not give any, because Tesla meter square is actually Weber. So this is Weber is correct. That's a unit for phi, or it is also a unit for N phi. Or we can also say Tesla meter square. And Weber per square meter. So basically Weber per square meter is a unit for B. How? Because the flux is equals to B dot A. So this is flux. How many field lines are passing through unit area? That is Weber. B example we don't know, and A is the area which is meter square. So meter square is there divided. So it will be Weber divided by meter square will be B. So Weber per meter square or Weber per square meter. So that is a unit for B. But they are asking for flux linkage. Flux linkage is basically N phi. So what is the unit of the phi? The same is there for flux linkage. That's why C is the right answer for this. So the unit of the flux linkage, again, the unit of the flux linkage or N phi, the same question. So it's not Tesla because a Tesla is unit for strength of a magnetic field. Tesla per meter square, that is not the correct unit for any of them. Weber is there because Weber is a unit for phi or N phi. N does not have any unit, so it's same as phi or N phi. Weber per meter square is a unit for magnetic field strength, not for flux linkage. That's why again C is the right answer for this. So in this question, a unit of magnetic flux. So magnetic flux or magnetic flux linkage have the same unit, so it's about phi, and we know phi is equals to B dot A. So it means it is Weber. There is one unit Weber, or because the unit of the magnetic field strength is Tesla and unit of area is meter square, so Tesla meter square. So magnetic flux is Weber, that's right, is the right answer. Weber meter square is not there, it is Tesla meter square. Tesla is wrong because it is a unit for B. Not Tesla per meter square, it should be Tesla meter square. So that's why A is a valid answer here. So in this question, the diagram shows three bar magnets are there, P, Q, and R. We drop them simultaneously and they fall through. So as they will move, they will have acceleration due to gravity. And as they're moving, their speed will change. As a result, when there's a speed is changing, there is a change in magnetic field. And due to the change in magnetic field, there will be an induced EMF. But that induced EMF can occur only in metals because induction or a current can flow through a metal, not for insulator. So plastic and copper, the cardboard, there is no change in there is a change in magnetic field, but there is no induced EMF. So for these two, what will happen? It will continue to accelerate due to gravity. But what happens, as we know, according to Lenz's law, that EMF induced always try to oppose the change. Like first, when the magnet is moving towards the copper, there is a change in magnetic field which induces EMF in the copper. As a result of this induced EMF, there will be a magnetic field of a copper and it try to oppose it. So how it can oppose? This side appear to be north and this side will be south. So when it is trying to oppose, there is a force on the magnet in opposite direction in which it is moving. So this acceleration will be smaller, acceleration will decrease compared to P and R. They will have the constant acceleration or speed will change at a constant rate. So the question is the order in which the magnet reaches the ground, because for cardboard and the plastic, they both have the same acceleration. So they will have the same change in speed. But in case of the copper, in case of this copper, what will happen? Because there is an induced EMF, that induced EMF try to oppose the movement of the magnet. So it's try to reduce its acceleration, or acceleration will decrease. So which one will hit the ground first? P and R will hit simultaneously and they are followed by Q, because Q is having a smaller acceleration compared to P and R. So option P and R simultaneously, they will followed by Q. So B will be the right answer for this. So in this question, there is a particle which is having a mass m and having a charge q which move in a circular perpendicular to magnetic field with a flux density of b. The graph shows a relation between the radius of orbit r and the velocity v. So they are directly proportional. What will the gradient? So how we can work out here what happened when object is moving in a circular path? So it means the centripetal force is equals to magnetic force. The centripetal force is given by a formula mv square over r, where r is the radius, m is the mass, and v is the speed. And when object is moving in a magnetic field, the charged particle is moving in a magnetic field. Force experienced by the charged particle is given by a formula F is equals to QVB. So when we simplify this equation, this speed will cancel with 1 of the square. So when we further simplify, this will be V is equals to QB R divided by M. Because R is divided, other side is multiplied, and M is multiplied, other side it is divided. Now we will compare with the equation of straight line y is equals to mx plus c, but because there is no y-intercept, so c is 0. So if on y-axis, but in this question, as you can see, instead of x-axis we have v and y-axis we have r. So it means the quantity r should be separated from others. So we'll simplify for r, because this is a simplification. This will be the case when on y-axis if we have velocity, on x-axis we have r, there will be a straight line and our gradient will be equal to qb divided by m. But because in the question r is on the y-axis, so we have to rearrange this equation. Like the original equation was mv divided by r is equals to qb. So when we simplify, r should be separated from others, so mv divided by qb is equals to r. Or I can also say this is r. So, or I can also say the r is equals to m divided by qb into v. Then I compare with the equation of straight line y is equals to mx. On y-axis, if I have r, the radius of the circular path. On x-axis, if I have the speed at which the particle is moving, so my gradient will be equal to what? It is equals the gradient g, if I say m or g is equals to m, the mass of an object, divided by qb or bq. So the gradient of the graph will be equal to m divided by b into q. So there is a current carrying conductor is there, which is placed in a magnetic field of 0.05 Tesla. That's the strength of a magnetic field. So we have B, which is 0.05 Tesla. The length of the wire L is there, which is 10 centimeter. We divide by 100, so 0.01. Sorry, 0.1 will be there because it is 10.1 meter. Then the force is about 2 into 10 power minus 3 Newton. That's a force on this. Which of the following is a current? So how to find a current? So we have the formula that force on the wire placed in a magnetic field F is equals to B. The strength of magnetic field I is the current and L is the length, and it is perpendicular. Whenever it is placed perpendicular, it means the angle is 90. So BIL sine theta, but this will be sine. The theta, the angle, because they are perpendicular to each other, so it will be 90. So F is a force which is 2 into 10 to the power minus 3. B is the strength of magnetic field 0.05. L is the length, which is 10 centimeter or 0.1 meter. I is the current, we don't know, that's unknown, and sine 90 is equals to 1. So this whole factor is multiplied, other side will be divided, so it will be 2 into 10 to the power minus 3 divided by 0.05 into 0.1. So when we substitute the values, the I will come out as 4 into 10 to the power minus 1 ampere. So we just have to use the direct formula to get the answer. So there are 50 turns and 0.06 is the length, n is the number of the turns, the magnetic flux density, B is there 0.4 Tesla. We want the flux linkage, so we need n phi, and because it is perpendicular, so where phi is equals to B dot A, that is the maximum when it is perpendicular. So it will be NBA, where n is n number of turns, that is 50. B is the strength of the magnetic field 0.4, and A is the area because this is a length, so it's, as they mentioned, it is a square coil, so it will be L square the area, so it is 0.06 square. When we solve this, the N5 will come out as 0.072 Weber. So in this question, there's a circular loop is shown. So a circular loop of a thin wire is there so that its plane is perpendicular to the magnetic field. So it is 90°. As a switch is closed, the loop of a wire, how to identify what will happen? If we know the direction of the conventional current, which is from positive to negative, so direction of conventional current will be like this in through the loop as the switch is closed, and it will pass through. So what you will do, you will apply Fleming's left hand rule. So when you apply Fleming's left hand rule, your first finger should point towards the magnetic field. So your first finger should point towards the right hand side. When we are checking, like example, if I say this is from A to B, the side of the loop from A to B, and then from B to C. So when we are checking from A to B, the force on that section, so first finger is representing a magnetic field which is toward the right hand side. So my index finger or first finger should point towards the right hand side. That's a magnetic field. The second finger represents direction of the current. So what happened to the current? When you check the current is pointing up according to the figure. So when you work out the direction of the force, you will find that the force is into. So this is the direction of the magnetic field. So this was the direction of the magnetic field. This is the direction of the current, which is up from A to B. Then what happened to the force? With direction we get a force, so force is into. So there will be a force into on side AB. Then when we check for side B and C, so for side B and C, the first finger represents the magnetic field, so which is pointing towards the right hand side. Second represent the direction of the current. The current should point downward as from B to C. And thumb automatically represent the force. So when you apply the rule, you will find your thumb is pointing outward. So force will be outward. Like this will be the direction of the force. So for side AB, the force is inward, basically toward the center. In terms of only if we take a section BC, then it is outward or towards us, and for AB it is into. So one side the force is into, the other side force is outward. So as, what will happen, because there's a force which is moving both sides towards the center, so as a result what will happen, the size of the loop will become smaller, so it will become a circle of a smaller radii. That's why A will be the right answer for this. So in this question, the diagram represents the two coils. So two coils are there, X, which is having 1000 turns, and it is having a cross-sectional area of 10 centimeters square. It is carrying a current which produces a magnetic flux density or strength of a magnetic field of 0.002 Tesla for coil, and there are 50 turns, and the cross-section is area is 4 centimeters square. We have to find the flux linkage. Basically what happened when there is a current in coil X, that current produces a magnetic field, and these magnetic field lines of the X are passing through Y as well. So we want to find the magnetic flux linkage for Y. So magnetic flux linkage for Y, which is N phi, where N is the number of the turns and phi is B dot A. So we can also say we need NBA. So the strength of the magnetic field of X is, because the magnetic field is produced by the X, and that is actually passing through, the field lines are passing through Y. So the strength of the magnetic field of X is what is passing through Y, and that is B, which is 0.002 Tesla. N is the number of the turns. So we need the number of turns of Y only. So Y is having 50 turns because we are finding flux linkage for Y, N phi for Y. So N is the number of the turns, which is 50. B is the strength of the magnetic field or field lines passing, 0.02, multiplied by area. But as you can see here, it is centimeter square, 4 centimeter square. So we have to convert into meter square because SI unit. So it is 4 centimeter square. We divided by, because to convert the centimeter into meter, we divide by 100. But this is centimeter square, so we'll divide by 100 square. So that is equals to 4 divided by 100 square, or 4 divided by 10,000 when we simplify. So it will become 4 into 10 to the power minus 4. So this will be equal to 4 into 10 to the power minus 4. That's our area. So 50 times 0.02 times 4 into 10 to the power minus 4. When you multiply all these factors, so when you substitute the values, so it will come out as 4 into 10 to the power minus 5 Weber. So in this question, the diagram represents two identical coils X and Y, and the plane of both coils are parallel to each other as their center lie on the common axis. The coil Y is connected to cell, so as you can see, it is connected to cell. A variable resistor and a closed switch. Under which of the following circumstances the current would induce in coil X? Basically, if there is a change in the magnetic field, then only it will induce EMF. And that should be in the same direction as the current shown in coil Y. So first what will happen? We'll use the right hand grip rule to find the direction of the magnetic field. If we use a right hand grip rule, so when we use the right hand grip rule, the fingers will turn in the direction of the current and thumb is pointing towards the north. So this side will be north and this side will be south. The field lines are from north to south. So we'll use the right hand grip rule. If we catch the wire in the direction of the current, where the thumb is pointing, that is the north. So north will be on the left and the south is on the right. So the coil are moved closer. If we move the coil closer, because if we move the coil closer, there will be a change in magnetic field of X. There will be induced EMF, but what will happen? It will try to oppose the change, and because according to Lenz's law, EMF induced always try to oppose the change in magnetic field. So when we bring the coil closer, the magnetic field will increase. So what this coil X will try to do, it will try to induce EMF, it will induce EMF, but try to oppose the change. And how it can oppose the change? By producing north pole on the right hand side and south pole on the left hand side. So it means option A, if the poles are produced are different or induced poles are different, it means the direction of the current will be different. That's why A cannot be an answer. When the switch is open, the moment we open the switch, as a result, what happened? If you open the switch, so this was north and south. So as a result, when we open the switch, the current, because current start to decrease in the circuit and until it is zero. So if this is a current graph, the current start to reduce or decrease. So this moment, when the current is decreasing here, according to Lenz's law, EMF induced always try to oppose the change. So if the current is decreasing, it means strength of the magnetic field is also decreasing. So what this coil X will try to do, it will try to oppose it. And how it can oppose this? By producing a current in a direction so that opposite poles are produced. So if it is decreasing, it will try to increase, or if it is decreasing or it is moving away, then it will try to increase. So it will be south pole produced here on the north pole produced on the opposite side. So B is the right answer. When the switch is opened, the moment we open the switch, the current start to decrease. So coil X will try to induce EMF in opposite direction. The resistance of a variable resistor decrease. If we decrease the resistance, the current will increase, and as the current will increase, it will try to oppose. So it will try to produce poles in opposite direction. So north will be here and south will be here. That's why C cannot be an answer. No change in arrangement. If there is no change in arrangement, there is no change in the magnetic field. So if no change in magnetic field, there will be no induced current or EMF in coil X. A coil of n turns, which is having a cross-sectional area A, lies perpendicular to the magnetic field. So it is perpendicular with the magnetic flux linkage X. So there is a coil which is having a cross-sectional area of A, and there are n turns, like n times the wire turns, and the magnetic flux linkage is strength of the magnetic field is B, and the magnetic flux linkage means the n phi is given by X. A second coil which is having a twice number the turns but half the cross-sectional area lies perpendicular to magnetic flux 2B. What will the magnetic flux linkage? So n phi we need for second coil. So they mention twice the number of turns. So it means the total number of turns, that is 2n. But half cross-sectional area. So area is A by 2. But twice the magnetic field strength, so it is 2B. So when we simplify, because n phi is X, or we can say NBA is equals to X. So when we simplify, this 2 will cancel with 2. So it will be, this 2 will be there in at the first. So 2NAB. And 2NAB or 2NBA, that is equals to X. So we can say it is 2X. So n phi is equals to 2X. So C will be the right answer for this. Is it clear, this question? So these are the multiple choice questions related to topic magnetism. The next session we'll do the structure questions.